Okay, next up on this demystifying climate models is on model evaluation and validation. I think you have some intuitive sense about what we mean by evaluation versus validation. Evaluation is about making sure that the model does what it is supposed to do, let's say just the seasonal cycles, El Niños, monsoon, and so on. And validation is where you are going to take specific data for specific events like a particular season of a monsoon, a particular El Nino, or El Nino frequencies, probability density functions, and so on, and see how model compares to reality. So there is a strong breeze again. Even though I have closed the screen, I can see that some wind is coming through, but let me check how bad the sound is. So here are the examples. Sparse, so this is sampled distributions. Points representing individual observations are randomly sampled from a distribution with a mean of 100 and a standard deviation of 2. Sample with 25 points. Probability distribution function here looks like this when you have such sparse data distribution, and when you have a well sampled distribution, then the probability distribution function has a much nicer, well defined shape, which means when you are trying to evaluate a model which has a certain resolution, as we saw, and is producing values at every grid point, data is often not as rich in space and time. And we have talked about how sometimes we mix or combine the sparse data in space and time with a model to produce what we call reanalysis products, which are kind of dynamically interpolated historic products that are often used for various process studies and sometimes even for model evaluation and validation. Okay, so probability distribution functions are shown here for different means and standard deviations of the distribution of a value of a particular variable. Could be temperature or rainfall, or and some of them, not all of them, have this kind of a Gaussian type distribution. Depending on the variable, they can have different distributions. So different symmetric distributions are shown here. Broad with the same width, black and blue. So these are just shifted, as we saw before, with the tails shifting when climate change happens, and the mean shifts, the distribution remains the same. And in the red, mean of 9 and standard deviation of 1.5. Black has a mean of 9 and standard deviation of 3. Blue has a mean of 11 but standard deviation remains 3, and so on. So one has to see if model can do these non-stationary climates as well. So typically there tend to be model intercomparison projects to see how a suite of models are doing. There are so-called paleo model intercomparison products, PMIP, C4MIP carbon cycle model intercomparison, and of course CMIP suite of reports that are used in IPCC, like CMIP 3, CMIP 5, CMIP 6, which are coupled model intercomparison projects where all the models are given the same set of forcings for historic simulations, like solar forcing, anthropogenic greenhouse gases, volcanoes, land use, aerosols, etc. And for the future, they're all given the scenarios as we saw, and then you see how the models do, and we will see how the models differ in the historic simulation and future projections, which is part of the model evaluation as well. So paleo data is of course mixed from various proxies. They're called proxies because even though you are looking at something like temperature, it's not measured with a thermometer in the past, but is inferred from something that is related to temperature. So we have instrumental records since about the Industrial Revolution. There are some borehole measurements that can estimate temperatures from 1500 AD. These are basically small holes drilled deep into the earth where some simple heat transfer models can be used to infer past data. Historical records, various estimates provide data back to 2000 years. Tree rings go go back to 8,000 years because either trees live that long or there are trees that have been preserving that record in some form. Ice cores of course can go up to 500,000 years, extended now over Vostok up to 800,000 years. Depends on how long the glacier has been growing and trapping bubbles which trap records of temperature, greenhouse gases like CO2, methane, nitrous oxide, and so on, with various uncertainties involved. Lake sediments over to 1 million years, coral reefs, ocean sediments, and coastal sediments can go up to a large range from 100 years to 100 million years. Okay, the time resolution of these samples can be very different. Tree rings and corals can have seasonal or even monthly signatures, whereas ocean and coastal sediments can have only time resolution of tens of years or less. Okay, so those are the kind of things one has to worry about. The other thing we have to worry about the models themselves is, of course, predictions and projections. We talked about initial value problem and boundary value problem. So weather forecasting we call the initial value problem because it is initialized with some uncertainty in the initial conditions themselves, because when you have a model, let's say it's a global model, at every grid point you have to have information of temperature, winds, humidity, and maybe chemistry, aerosols, land use change, and so on, or land use for integrating forward even for a few hours. And there is the current climatology that is observed. We call current because this can evolve because of climate change. And then there is the space of forecast uncertainty, in the sense that the current climatology is here and model perturbed initial conditions, what are called ensemble members, are going over this range. So small differences in forecasts are ending up with large differences in the small differences in initial conditions are ending up producing large differences in the forecast for observed variable. This is what we said about chaos and nonlinear effects of the system, where small errors can lead to very large errors in forecast by a few days. So there is limitations to weather. So schematic of a probabilistic weather forecast using initial condition uncertainties. The blue lines show the trajectories of individual forecasts that diverge from each other owing to uncertainties in the initial conditions and in the representation of subgrid scale processes in the model. So when we have a dynamic model, it has equations to solve for momentum, mass balance, energy balance, and so on. But things like convection and clouds are parameterized, and even when there is an equation, mixing and other things within a grid, what is called subgrid scale, are not explicitly represented because quantities being advected and mixed are grid averages. So often there are subgrid scale processes like eddies and fronts and so on that are not represented, so they are parameterized with their statistical properties, so that can add uncertainty as well. In the dashed lighter blue envelope represents the range of possible states that the real atmosphere could encompass, and the solid dark blue envelope represents the range of states sampled by model projections. So when you make forecasts, you know there is a climatology, and if the model says tomorrow will look like climatology, then the model is not considered skillful. When it deviates from climatology, then it is indicating a signal, and of course that signal can have large uncertainty like this. So this is a forecast uncertainty. So model evaluation has to understand the model uncertainty itself based on either initial condition uncertainties or subgrid scale process parameterization in the model. The same thing when we integrate longer. I can see some strong wind here, sorry if there is a noise. you can see that there is the climatology again. There are initial conditions, and there is our forecast uncertainty. But forecast uncertainty with model bias is shifted over here. So model can have systematic bias in the sense that, let's say, in the monsoon regions, models typically tend to rain less than climatology. So when you do seasonal forecasts, typically you don't say it's going to rain 800 millimeters if that's the climatological amount of rain, but you tend to say rain will be above normal, below normal, or normal. So you tend to say some anomaly. So some model bias can be taken care of when you say you're only saying excess rain, deficit rain, or normal rain, because you are only talking about with respect to the model climatology itself. So model bias is in some form taken care of. But when you do longer term decadal time scale projections, the climatology in the real world itself may shift because of, let's say, global warming, and then you have the model climatology with bias here and the uncertainty going here. So schematic of ensemble prediction system on seasonal to decadal timescales based on figure 1, which is what we had looked at, showing the impact of model biases and changing climate. The uncertainty in model forecasts arises both from initial condition uncertainty and model uncertainty. So when we do forecasts, we are initializing and integrating forward, whereas typically climate projections out to multiple decades are not forecasts, they are projections. They are not predictions. So they are started with, let's say, pre-industrial level of CO2, integrated for several centuries sometimes to equilibrate the model climate to reduce the model climate drift and so on, and then integrated forward into the let's say 19th and 20th centuries, and of course beginning of 21st century, with increasing greenhouse gases prescribed, land use change prescribed, solar changes specified, volcanic forcing specified, and so on and so forth. So those are not predictions, they are projections. So there is different ways of thinking about those. The example from this paper by Julius Lingo and Tim Palmer is now showing examples of partitioning of the uncertainty in projections of Southeast England rainfall for the 2020s and 2080s using some model, UK model. So here you see that in the historic in the 2020s, you have model uncertainty of 25%. Carbon cycle is adding a little bit here. Natural variability is a large noise in the system. When you're making future projections, natural variabilities modify the trend because of scenarios and changes in greenhouse gases, and you have the downscaling error because it is being done for Southeast England. You prescribe the boundary conditions and downscale, which itself is adding some error. So when you go to longer time scale, model uncertainty here is estimated to be larger, and the natural variability contribution to this uncertainty is reduced by then, relatively speaking, when you look at the anomalies in the 2080s. Okay, and carbon cycle is larger here, and the downscaling error is reduced as well. So if you don't get an intuitive sense about this, don't worry about it, because forecasts are done this way. This is actual forecast now for this year 2022, going from April into March, April, May, June, May, June, July, and so on. And these are the multiple models doing the forecast. Some are dynamic models and some are statistical models. Sorry, I will try to reduce the noise by doing this, but the wind is really strong and blowing right through the screens here. A lovely cool breeze, but I'm sacrificing myself because I want to record these podcasts right now. So you can see that the various models are starting from the same initial conditions and then going off in very different directions. Negative Nino 3.4 here is of course La Nina, and when it goes positive it is El Nino, and there is one model BCC CSM whatever that model is going gangbusters and saying there is an El Nino coming, whereas most of the others are saying this year is going to stay in a La Nina. And when multiple models exist like this, typically evaluation of the forecast is done often for either a dynamical average here or a statistical average for these models, and skill of the forecast is assessed by taking such forecasts over the years and correlating with observations after the event has passed, and then see what are the skills, and anything with more than 0.6 correlation between observations and forecasts are considered very useful, usable, and so on. So this is a model evaluation in the forecast sense. When you want to do the evaluations for projection models, which are not forecasts, as we said, we have to worry about natural variability, which, as we said, can add uncertainty. So this is natural trends in temperature in degrees Celsius. So you have things like El Nino happening here in this red line, which produce mini global warming, as we said. Amount of radiation because of solar activity is changing as well, and volcanoes are hitting the system with radiative cooling, especially when a strong one happens like this in 1991, the Pinatubo over Philippines, and so on. So the models have to worry about these perturbations from the forcing and the associated radiation balance, energy balance, and so on. But together, when it is done for a long integration through the 20th century into the 21st century, there is a historical period over which the observations are compared with multiple model spread, so you can consider those as model uncertainties, and the idea is that the model ensemble in this white line is closely tracking the observed warming trend, so that's very encouraging. It gives you confidence for the future. But when you integrate into the future, the uncertainties come from internal variability, so that's the El Niños, La Niñas, and all these modes of forcings we talk about, and there is a spread due to the models like these that are going into the future, and the scenarios themselves are going to create uncertainties. So you can see that in the beginning, internal variability and model spreads dominate the uncertainty plume, and as you go into longer decades, longer into the future, scenario uncertainties begin to dominate our projections. So these are the ways to think about, and this is for CMIP 6, which just came out, or this is CMIP 5, RCP's various representative concentration pathways, 2.6, which represents the radiative perturbation at the top of the atmosphere by 2100 if we follow this pathway of technology, population, renewable energy, policies, and so on. It's a good one to stay below 2 degrees C by 2100 with a 67% probability, for example. And these are the number of models that simulated that scenario for the future, and you can see that they produce this range of temperatures by 2100. And the RCP 8.5, which is the business as usual scenario where we hardly do anything to mitigate climate, then we end up in this upper range with 39 models producing this range here of warming compared to the 1986 to 2005 period. So we are always dealing with multiple models and their own uncertainties and how they respond to the forcings that are changing into the future. So these models are also validated for the past, so going for a millennium or two, and then looking at the industrial period and then looking at how they do. So they can reproduce the observed warming when all the four things are given that we looked at: volcanoes, aerosols, land use, solar, and so on, greenhouse gases. Models can be used for attribution, which means if we take out all those human-induced greenhouse gases, then the models say there would have been no warming. So this is another use of models in terms of evaluating and validating them, saying once we are sure that they're doing a good job of the warming observed, then we can take out the human forcing and say the warming is almost entirely due to human emissions and so on. And patterns are checked this way. So historically there's been about a degree C warming since about 1850, and you can see this is the observed estimate of the spatial pattern of warming, with this warming hole here related to the Atlantic meridional overturning circulation that we talked about. Warming is higher because of the polar amplification and the snow albedo feedbacks and cloud water vapor feedbacks and so on here. And you can see that the models do a reasonable job with minimum warming here, maximum warming over there, and so on. So the spatial distribution of warming and regional trends are also reasonably done by these models, suite of models. So this is how we evaluate and validate models. Okay, this podcast is a bit long, but it's quite descriptive, so I hope it's useful for your purpose.